gonna cool it down.
I think I know what's gonna happen.
Very, 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 very cold.
Yeah, I think I know what's gonna happen.
Specifically, you think you might know what's gonna happen? Well, don't spoil it.
There's liquid nitrogen.
I'm gonna switch
Super
my
cold.
super science glasses of science here. I'm gonna cool it down to liquid
know what's
nitrogen.
gonna happen.
Has anyone seen or used liquid nitrogen before? A couple. A couple. So what I've got here, these are cryo gloves. Cryo just means cold. Liquid nitrogen is so cold that
Don't touch it, Maxie,
you
you'll
can't touch
die.
it with your hands. It's so cold it will burn you.
Is it like, wait, is it like that ice was so hot? Dry ice?
So close. Dry ice is made of something called carbon dioxide. It's solid carbon dioxide. This is, as the name implies, liquid nitrogen.
I know what's gonna happen.
It will break your finger off, Maxie.
Do not touch, do not touch.
Maxie,
You
come
can
back.
touch the,
Maxie,
the
come
smoke.
back.
And I'm gonna ask everyone stays behind this line, so
Maxie,
please back up, please
come
back
back.
up, please back up, please back up.
Come,
Little more,
come,
little more,
come
behind
back.
that line. There you go.
And if you guys
Kai, come here.
You have to be specially
Don't get
trained in
close to
order to use this chemical, that's why.
It's very cold.
You see her?
It's very
You see her
cold.
wearing gloves?
I know what's gonna happen.
It will break your
I
fingers.
know what's gonna happen.
Okay, don't spoil it. So, we are gonna do a science experiment here today. We have our racquetball that is now being dunked in liquid nitrogen. Does anyone want to guess how cold liquid nitrogen is?
Very cold. Colder than the ice
297 what?
No, it's like very cold.
Fahrenheit.
It's
So you're close.
steaming.
It's actually, well, close, but in the opposite direction. It's, yeah, do you want to guess? Yeah, you're actually very close. So, liquid nitrogen is negative 321 degrees
I know
Fahrenheit.
what I was gonna say.
Very,
Back off a
very
little bit.
cold.
Back off, back off. Back off.
So what we're going to do today, like I said, I study a material at normal temperatures. And then I change its
Backing off,
environment.
backing off.
And then I study its properties
Back off.
as it's changed from the change in environment. So in this case, I'm cooling down our racquetball. And then I'm going to repeat our same experiment where I dropped our racquetball and we're going to see what's going to happen. So since we're scientists, we like to make hypotheses. Does anyone have a hypothesis as to what might happen when we drop it? And if you've seen this demo before and you know what's going to happen, I'm going to ask you to lower your hand to not spoil it for everyone else. Okay, what do you think is going to happen? It might not bounce. You think it might break? What do you think? Okay, so some people think it's not going to bounce. One person says it might break. Anyone think it's going to bounce really, really high? Maybe some people? Okay, so
Back up, back up.
now
In my
we've
bounce.
made our hypothesis, but now comes my favorite part about being a scientist is actually doing the experiment. So you all ready?
I know what's gonna happen.
Okay, so I've been known, I'm not very coordinated because I'm a scientist, I've been known to miss this plate before, so hopefully I'll actually hit it this time.
Come here, Maxie.
Okay,
Back up, Maxie.
hopefully this is
Just
good
in
enough.
case.
Gotta make sure it gets really, really cold. Okay, you ready?
Focusing.
Okay, I think this is good enough. I hope so.
We'll find out.
I know, we'll find out. All right, ready? 3, 2, 1.
Don't touch it, don't touch it.
No, they can touch it.
Oh, touch it, dude.
They can touch it.
I would avoid touching it for another like couple minutes or so, just because it's kind of cold. Here, I'll grab it.
It actually gets cold. It's fine.
Oh, we're good. Okay.
It's fine. Yeah.
What happened?
Go ahead.
Come in, come in.
It's cold.
Of course, sorry.
For those of you paying attention, what did it sound like? Sounded like glass. Does anyone know the material property that we call when it shatters like this? It's the opposite of ductile. Anyone know?
Ductile?
Brittle. Yep. We call this brittle.
Brittle.
What happened? Whoop, as I step on my materials. We're good. What happened?
It shattered.
It shattered. So, what happened was the molecules inside the racquetball, when we cooled them down, changed properties. The molecules themselves changed how they were arranged because it it was super, super cold. So that when I dropped
Ooh, super cold. Let mommy touch it.
I
did. You want to touch it?
And it shattered instead of bounced.
Ooh, let's try it with a shoe.
What?
Ooh, a tennis ball.
Tennis ball.
What? So this isn't ice. This is nitrogen. It's a gas. Well, not right now. It's a liquid, but usually it's a gas.
Ooh, look,
Okay.
try a tennis ball.
We are going to repeat the same experiment. But
I've never seen that.
with a tennis ball.
Yeah, please, please.
I will tell you, and this is actually verified. We experimentally verified this. The tennis ball is the same material as our racquetball, the same polymer. I'm going to repeat the same experiment. Some people say it's not looking good for our tennis ball.
It's dead.
So, we have our tennis ball. It's in the liquid nitrogen. Someone give me a hypothesis of what you think will happen. Yeah, it's going to break. What do you think?
It might actually end up different.
It might end up different. Okay, what do you think? It's going to bounce really high. Yep. Uh-huh. Keep that idea. So we have a few different ideas, few different guesses. Once again, I'm going to make sure this is very calm.
Maxie, back.
You think it's going to break? Okay, well, again, my favorite part of being a scientist is doing the experiment. Only one way to find out. Okay, we're going to do another 3, 2, 1. You ready?
Okay, stand up, Maxie, stand up.
And
Kai, back up a little bit, Kai.
Back up.
Back
okay,
up.
drop test. 3, 2, 1.
Oh! Oh!
What happened?
It didn't break.
Did it break?
No.
So now, it does kind of look like a comet, doesn't it? Do we have a piece of material? Okay, now I want you all to think like a scientist. What happened? What is different between the racquetball and the tennis ball that might cause the racquetball to break, but the tennis ball not to break?
What do you think?
It has fuzz, exactly. Yeah.
Right there.
Yes, you're exactly right.
Young. Watch for him. I
So
don't
they're
know
both
when he's
hollow
gonna reach. No, Maxie,
inside.
holding them.
He knows.
Different color.
Different. I love that idea, but not quite. Thank you. I know, I've already done that. They're both squishy.
But it's fine, pause it.
So I will tell you that a few folks in the audience were right. The tennis ball has furries on the outside, but the racquetball does not. In science, we say that the tennis ball has a high surface area, which means that there's more stuff on the surface of the tennis ball, and so, but the racquetball is very smooth. So when I cool down the racquetball, take it up, drop it on the plate, it's still as cold as it was when it was in the nitrogen because there's not enough things on the surface for it to warm back up. But our tennis ball has all those little fuzzies and fibers. It's got a high surface area. So when I take my tennis ball and drop it on the plate, by the time it hits the plate, it's already warmed up too much and it won't break like the tennis ball did. I've got another experiment for you.
Ooh, chicken McNuggets.
Where's got my balloon? Balloon guy. Yeah, thank you for holding that. Okay.
Oh, balloon. See, right?
Now.
Maxie, she's gonna freeze a balloon. Maxie,
I've got my
freeze a
balloon.
balloon.
And I'm going to drop it
No
in the
pushing,
nitrogen.
Maxie. No
Don't get
pushing.
close.
You ready? Let's see if it's happy. Okay. You think it's going to shatter? You think it's going to pop? I don't know. Let's find out. You ready? Ready? What? Let's go. Okay. 1, 2, 3. Uh-oh.
You wanna go in front of her?
What? What's happening? It's not breaking. In fact, it's getting smaller. Is that what you expected? the air is getting frozen. Someone tell me, why is my balloon getting smaller?
Because hot air, like a hot air balloon,
Yep.
it rises up
Yep.
and spreads apart.
Yep.
Cold air,
You're exactly right. But it comes together so much that it undergoes a phase change. Someone tell me what a phase change is. Anyone worried about the states
Guy
of
doesn't know
matter?
what the face change.
So he put his hand
Yeah,
down.
tell me what are the states of matter. Solid, liquid, gas, bingo. What happens if we take liquid ice and cool it down? Oop, if we cool it down, make it really cold? I said liquid ice, I meant liquid water. Sorry guys, not enough coffee today. If I take liquid water and I cool it down, it's gonna turn into a solid, right? So if we have air and we really, really, really cool it down, what's gonna happen? Is it gonna stay? Oh, sometimes that works, sometimes it doesn't. So you see at the bottom? Was that in the balloon when I blew it up? Look at that liquid in the bottom. But now, what's happening? It's getting bigger again. Someone tell me what just happened.
See, it's getting bigger now.
I know.
What do you think?
It's not cold.
Condensation. I actually love that answer. What? All the air is warming up again. Specifically though, what?
That's good,
What
Kai.
in my balloon? What was the liquid that you saw? Sometimes I can make it into a solid, which is why I hit it against the plate. What was that liquid that you saw in the balloon? Not oxygen, not nitrogen.
Water.
Water. Bingo. We have water vapor in our breath. And so when I cooled it down, it turned into a liquid, and if I left it long enough, it would turn into an ice. So you think, wow, this is all very cool. Get it? It's all thank you.
Very
It's
cool,
all
very
very
cool.
cool. But what is the application? Because I do research, I'm a scientist, but I'm also an engineer, which means I like applications. So what is the application of freezing stuff and then smashing it? Other than it's very fun. Somebody tell me what happened to the Titanic. It hit an iceberg and it sunk. The reason it hit and I'm going to give a disclaimer actually real quick. If there's any material scientist in the audience, yes, I know it's not exactly the same. It's close enough. Close enough for this demo. So what happened was something very similar. If we know the Titanic hit an iceberg, what can we infer about the water? What temperature? Who said it was cold? Yeah, it was cold. Cold enough to form an iceberg. Cold enough so that the metal that the Titanic was made of changed properties. It was so cold that in normal, warmer waters, if you bent the metal, if you hit the metal, it would dent. But if you cooled it down and you hit the metal, it's going to shatter, just like our racquetball did.
Kai.
Does anyone, any older folks in the audience, any adults know about the Challenger explosion? Does anyone know what happened in the Challenger?
You want to do this experiment?
What happened? Wow, yeah, you're exactly right. Good job. So the Challenger explosion, the reason why the Challenger exploded was because of O-rings. O-rings are very teeny, squishy rubber. But the Challenger, the morning of the launch, was too cold. The same thing with our racquetball happened to the O-rings in the Challenger. And when they had little fractures, they didn't seal properly, which means chemicals that were mixing should not have been mixing, and that's what caused the explosion. So, material science is very, very, very important, and it's why everything around you works the way that it does. So please stick around if you have any questions about nanotechnology. Again, I'm Abby from Nano at Stanford. Thank you all so much for your attention.
Yeah. What would happen if you put hair in there?
It's the liquid nitrogen. You can touch it.
What happens if you put hair in there?
I don't actually. Oh yeah, you're good. I don't actually know. I don't know. I guess it would probably get kind of rigid. I don't know. I've never actually tried before. Yeah.
You are very good. Thank you.
Thank you.
Okay, guys.